Excellent. Very good. Welcome back, everybody. So this is a recap of this topic that I call topic 3 within the thermodynamics module. And where we stand is that in the prior topic, we discussed a number of different ways in which molecules can interact with each other. Dispersive interactions, electrostatic interactions, dipolar, and so on and so forth. And at the end of it, we classified them and we figured out which ones are the most important and how we can, decide what to include or what not to include in our analysis. Now the question is, do we believe those results? How do we validate those potentials that we can use? Like the Lennard-Jones potential, for example. Is it good or is it bad? So today, what I want to do is to go through the one way in which you can try to see if the potentials make any sense. The material that I take is from the 5th chapter of Prausnitz, and of course I put current literature to make our discussion a little bit more current. So let's see what we have. First, we need to talk about fugacity. So what we saw is that when we are talking about equilibrium, what we need to do is to impose that the chemical potential of a component, say component I, in the gas phase is equal to the chemical potential of that component in the gas phase. And that has to be true for every component that we have in a mixture if we want to describe the properties of equilibrium. All right, now, what is different compared to what is written here and what I said is that I wrote the letter F here, which stands for fugacity. So basically what we are doing is that instead of talking about chemical potentials, we are going down and introducing fugacity so that we can express this fugacity in terms of composition of the system, which as engineer may be what we care about. Now, if we go back to classic thermodynamics, it turns out that, and I will not do the derivation, it turns out that we can express the fugacity of a component in a mixture by this equation over here, where the fugacity coefficient is defined as described over here. It's the ratio between the fugacity and the mole fraction over the pressure. And here we got the partial molar volume of the component I in the mixture. This is the definition of the partial molar volume. And RT and the pressure is the pressure of the mixture. So what we need to do here is the integral of this quantity all the way from zero pressure to the pressure of interest. So if we are able to describe this partial molar volume, so essentially if we know how the volume of our mixture changes with pressure, temperature, and composition, and if we know how that volume changes all the way from zero pressure to the pressure of interest, we will be able to differentiate and calculate the partial molar volume, and we will be able to solve that integral. We will have to do it for the component when it is in the gas phase, and then we got to do the same derivation for the component in the liquid phase. So that equation has to be valid all the way from zero pressure to the pressure of interest, and it also needs to be able to do that phase transition. If that's the case, then we are able to, by applying that equation, calculate exactly what is the fugacity of that component in the mixture. If you go back to the Prausnitz book, what you can see is that you can express the same quantity in a different way, but now where we are basically now expressing the pressure of the system as a function of the composition, the temperature, and the volume. But the principle is exactly the same. Now, what we need to do is to be able to express this pressure all the way from a volume that is infinite, so very low pressure, zero pressure, all the way to a volume that is the volume of the mixture that we are interested in. So again, we need to have this equation that is going to need to be valid all the way from infinite molecular infinite molar volume of the mixture all the way down to the volume that we're interested in. And in this equation, what we see is that we are introducing this parameter Z, which is the compressibility factor of the mixture. I use a small volume here to indicate that it is the volume of 1 mole of that mixture, right? So everything seems to be fine. You know, it's just a matter of being able to differentiating and integrating equations. There are software these days that do it for you. The problem is that for this derivation to hold, we need the equation of state, which is the relation between the pressure and the number of moles of our components and the volume and the temperature. This equation of state has to be valid all the way from zero pressure, the ideal gas limit, all the way to the pressure that we're interested in. And it has to be valid for all the system composition that we're interested in as well. And notice that because we are doing the integral, if that equation is not valid in a small range of that very extended range of pressures, that deviation between reality and the equation in that small range will be leading to errors because you're calculating an integral, right? So this equation has to be true, and it has to be very close to the real data, and it has to be true for all the system compositions that you're interested in. Now, if you look at the literature, you will find many equations of state. A group in Imperial College led by George Jackson, Amparo Galindo, and their collaborators, they are excellent at deriving new equation of states for some systems. Now they're focusing on the pharmaceuticals, if I remember correctly, and that's great. The problem is that if you come up with a new component, if you work for a pharmaceutical company that wants to study a new component, you will need new parameters to be put into that equation of state, should that equation of state work. Many times we are interested in systems in water, and it's very difficult to describe the properties of water using equations of state. So again, we are in trouble. And many times we need experimental data. And if we look at the literature, we find experimental data for 1, 2 components. But the moment we're interested in systems that have 3, 4, 5 components, the data becomes very, very sparse. So it is very difficult to validate the equation of state, right? So the problem is solvable, but we don't have enough knowledge, enough data to be able to solve it. And the issue is that we are always interested in new materials. So even if we spend 10 years to derive an equation of state that is of interest now, in 10 years down the line, companies may be interested in new components. So we are always doing a catch-up type of exercise. So the purpose here is to try to see if that understanding that we developed earlier regarding the possible interactions between molecules could help us via the molecular physics, statistical mechanics approach, could help us predict what are these equations of state so that we can then use these equations that we just discussed to extract the fugacity of the component in the mixture, right? So that's the key. So let's consider for a moment one equation of state that you have seen before, the virial equation. And the reason we do that is that you are familiar. It's a very simple equation. Probably it was the first equation of state that you saw. It's so simple that we know that it is only valid at low densities, and so we tend to discard it because it's so simple. The thing is that this equation is very, very important because the parameters in this equation are actually directly related to the interactions between molecules. And if you remember, what the statistical mechanics want to do is to relate the interactions between molecules to the equation of state, for example, to how the macroscopic manifestation of a system look like. So ideally what we want is an equation of state in which there are parameters, but we want to be able to describe those parameters depending on the properties of the molecules in that system. So for example, the size of a molecule, the dipole moment, polarizability, and so on and so forth. All right? So let's go back to some experiments. So this is the compressibility factor of a mixture plotted as a function of the molar density. So what you see, and there are several systems in this graph. There is helium over here. There is methane is probably this one over here. and this one here is 50% water in methane. Okay, and what is, so basically there are pure components and mixtures, and what you say is that even though they are very different systems, they all converge when the molar density goes to zero. So basically when the pressure goes to zero, when all of these mixtures behave like ideal gases, all of these data points converge to compressibility factor equal to 1. So this is the definition of the compressibility factor. You notice that it reminds you of the ideal gases law. So it's the ideal gas law applied to one molecule. And what you see is that every single system, when we are at very low density, behaves like an ideal gas. But then the moment we start increasing the densities, what you see is that in some cases, the compressibility factor decreases. In other cases, it goes up. And in other cases, it has some sort of inflection points. Okay? So whatever equation of state we pick, if we want that equation of state to be able to be used in those equations to extract the fugacities, need to be able to describe all of these trends all the way from the low densities conditions to the conditions that we are interested in. So that equation of state has to be able to reproduce these curves. Okay? One equation of state is the virial equation of state. It's very simple. It is expressed as an expansion of this compressibility factor. It can be expanded as 1 over the molar volume or as the pressure. They are equivalent, and actually the B and the B primes, they are related to each other. The C and the C primes, they are related to each other. And the reason is that it is the same equation. Okay? So this is the virial equation. It is an expansion. It is a series expansion. The more terms we have, the better we are at describing all the properties of the mixture that we are considering. But of course, we will have limited accessibility to data. So many times we just truncate the virial equation to this B term, or sometimes we may be able to get enough data to extract the C term, right? So what are these B and C? The B is known as the second virial coefficient, the C is the third virial coefficient, and so on and so forth. They are not dependent on the pressure or the density. So once we know them for a given conditions in terms of pressure, they hold at that pressure. But for pure component, they do depend on the temperature. And for a mixture, they depend on the mixture composition. The very big advantage of the virial equation of state is that it is reproducing experiments at low densities, but statistical mechanics is able to tell you what the second virial coefficient, the third virial coefficient, and so on and so forth should be if you know what are the interactions between the molecules. Okay? So if we know how these two molecules interact with each other using statistical mechanics, and then we show you how, tells you how you can extract the second virial coefficient, the third virial coefficient. So you're basically able to reconstruct the equation of state. That's the big advantage. How do we extract these numbers? Well, if this is the equation of state, notice that I prefer to use the expansion on the molar density. And the reason is that for the same number of parameters, this version of the equation allows you to get a little better reproducibility of experiments compared to the one explicit in the pressure. Now, but anyways, if you're looking at this equation, what you can see is that the B parameter is the limit for the density that goes to zero of the partial derivative of the compressibility factor, and this other limit tells you what the third virial coefficient is. So if you have a lot of data, you can calculate these B and C by doing the differentiations. Back in the days, it was not so easy to do derivations and so this type of analysis because computers were not available. So what people did was to do a lot of graphical extrapolation of the terms. And the way you can do it is to say, okay, let's give up our hopes to be able to fit the D. So let's just stop at this term over here. So this is our virial equation of state. Now what I do, I take this one and I bring it to the other side. And so the equation becomes this. And now what I do, I can multiply left and right by the molar volume V. So now my equation looks like this. So now if you collect experimental data, what you can do is to plot on the y-axis, you can plot this amount. And on the x-axis, you can plot 1 over V. So you can plot this amount on the left-hand side of the equation as a function of the molar density. And then what you will see is that you should have a line, and the intercept of that line with the y-axis is going to give you the B coefficient, and the slope of that line is going to give you the C coefficient. So this is how it looks like. This, you plot here the left-hand side of the equation. On the x-axis, there is 1 over the molar volume. These are the experimental data for a pure component, for a mixture of a given composition. And what you see is that the intercept in the y-axis tells you what the B coefficient is, and the slope at the limit at low density tells you what the C coefficient is. If the equation was good, able to reproduce all the experiments, what you would have is that the experimental data will be aligned to this straight line at larger densities. In reality, what you can see is that there is already a deviation over here. And the reason for that is that in this approximation, we stopped at the C parameter. We did not consider the D. So we are only able to capture the behavior of a system up to medium densities. All right? So in other words, the virial equation of state truncated at the third virial coefficient is good, but only up to reproduce the compressibility of a mixture of up to 1/2 of the critical density. If you go up near the critical density, the representation becomes fair, and then it becomes poor if you go to larger densities. Here, what Prausnitz does in this figure is to show you the comparison between the experimental data, this curve here, and what the virial coefficient does tell you. So in this expression here, this one here that I indicate with the dot line, is the virial equation to the third virial coefficient as a function of the molar density. And what you see is that up to here is pretty good at reproducing the experimental data. The other curve, this one that I do in a continuous line, is again the virial equation of state, truncated at the third virial coefficient, but now in the expression that is explicit in the pressure. And what you see is that it is only able to reproduce experiments up to here. So much lower densities compared to the other expression of the virial equation of state. So that tells you that if you can choose, you should pick the virial equation of state expressed in the molar density to get larger range of experimental data to be reproduced by your equation. Okay? All right. Now, why is it that you need more and more coefficients to describe better experimental data at larger densities? Well, the reason is that at low densities, when you have only a few molecules in the system, only binary interactions, the interaction between pairs, are going to be important. These interactions between pairs are also important at intermediate densities, but here you also have interaction between triplets of the particles that are important. If you now go to larger densities, a little bit closer to the critical point, pair interactions are still important, triplets interactions are still important, but now because the molecules are very close to each other, you will need to take into consideration interactions between 4 particles at a time. All right? And the interesting and useful thing about the equation of state is that the second virial coefficient describes interaction between pairs. The third virial coefficient, so that was B. The third virial coefficient C describes interaction between triplets. And the fourth virial coefficient describes interaction between 4 particles. And that's where the names come from. Second virial coefficient, pairs. Third virial coefficient, triplets. Fourth virial coefficient, 4 particles at a time. All right? So if we want to describe systems at very low density, the second virial coefficient will be enough. But then at intermediate densities, we need the second and third virial coefficient. But if we want to go to larger densities, we will need second, third, fourth, and eventually fifth, and so on, virial coefficients. All right? So that's the reason why this equation of state is attractive, because actually there is a clear meaning of what those parameters look like. And what we will see soon is that statistical mechanics tells us how we can get those parameters from knowing what molecules we have in the system. Right, before I go there, I leave you with a paper that is in the current literature. This is a paper from a number of years ago from Peter Cummins and this group. And Peter was my postdoctoral supervisor when I was at Vanderbilt University. And so I worked with him for a couple of years or even more. And what they did in this paper, they simulated a fluid that was composed of hydrocarbons. And what they did was to see the difference in behavior of that fluid when it is in the bulk, or when it is confined in between two solid particles that are parallel to each other, so atomically smooth. And the distance between those two particles was decreased from a large number of values all the way to an integer between 2, 3, 4, 5 times the diameter of one of the little spheres that made up one of these chains. And what you see here is that at these conditions, when there is there are 3 layers of the hydrocarbons in between the two solid particles, what you see is that in the top view tells you that you have a very nicely ordered structure of the fluid inside of the two solids, whereas on the outside you have very liquid-like behavior. So in other words, confinement can drive a transition between a liquid and a solid when the confinement is atomically smooth and the distance between these two flat surfaces is less than, I believe the critical number was 6, less than 6 number of layers, and you have a very nice solid structure. So take a look at this paper, and I think it is fascinating because as we move into nanotechnology, we make things that are smaller and smaller, and these things do approach each other at some point. They may be atomically smooth. So it is possible that when we expect things to behave like a liquid, they are actually behaving like a solid. All right. Now, let me take a sip. We discussed that this virial equation is useful because there is a direct link with the statistical mechanics. Well, that link is expressed by this equation over here, where B is the second virial coefficient, and this is the Avogadro number. This is a constant pi. This is an integral from distance 0 all the way to infinity. R is the distance between two particles, radial distance essentially. And what we have here is that the 1 is just a number, the exponent of minus K is the Boltzmann constant, T is the absolute temperature, and this here is minus the potential energy, the interaction potential between two particles that are separated by distance r. So essentially, if we know how two particles interact with each other as a function of the distance between their centers of mass, we can plot that function inside of this integral, and by calculating the integral, we know what the second virial coefficient is. So this is the one that we use the most, but statistical mechanics also tells us how the third virial coefficient looks like. Of course, it's a more complicated equation, but at the core of it, there is the pair interaction between the molecules in the system. There is an assumption here, and that assumption is that we can describe interaction between triplets as the sum of the interaction between the pairs that make up the triangle. It can be an assumption that induces an error. Sometimes it has been estimated in 5 to 15%, depending on the configuration of the triangle. But in general, other than that, it's not a very strong assumption. But please do remember that this is the assumption that we have when we solve this equation over here. So this is the assumption that is being made, that the interaction potential between the three particles is the sum of the three pair interactions. The statistical mechanics does not need to make that assumption, but we need to do it if we want to simplify the statistical mechanic equation into that form that may not look all that simple once it is written there. But if you do know how the interaction potential between pairs change depending on their distances, all you need to do is to have patience to solve those nested integral with care. Okay? Now let's go back to this. So the virial equation of state is valid for all stable, electrically neutral molecules that do not go into chemical reactions. The in these expressions here, what we are doing is to assuming that the interaction potentials are spherically symmetric. So we know what the distance between the centers are, but we are not really looking at the different shapes of the molecules. If there are different shapes and different orientations and so on and so forth, then we do need to take that into consideration as well. Okay? We saw earlier that we can extract the experimental virial coefficients from experimental data. If you want to do this process for mixtures, you will obtain the second and the third virial coefficients for the mixtures, but keep in mind that the data need to be at the same temperature, and they also need to be at the same composition, because the parameters, the B and the C, they do depend on temperature and they do depend on the composition. Right? So here is some experimental data for a methanol methyl acetate equimolar mixture, so 50-50. And what you see here is that the mixture composition is always 50-50, but what changes is the temperature. And as the temperature increases from 120 to 160 Celsius, what you see is that the compressibility factor increases in this order, and the B parameters, which are the intercepts, increases as well. All right, so do keep in mind that the temperature affects the second virial coefficients and the third virial coefficient and so on and so forth. If we are interested in extracting the second virial coefficient for a mixture, what we can do is to apply the same equation we saw earlier for the second virial coefficient. Everything is the same, except that now in this expression here, we need the pair potential between the two particles, the I and the J, as a function of the distance between the centers of mass. Everything else is the same. But notice that this equation here only tells you the interaction potential between I and J. It does not tell you anything about what is the composition of the mixture. So what happens is that if you have a binary mixture, what you do, you extract the second virial coefficient for that binary mixture, knowing what is the second virial coefficient that represents interactions between II, JJ, and IJ molecules. So in other words, we need to do these calculations here to find out what BII is, what BJJ is, and what BIJ is. And then by knowing what the composition of the mixture is, you can apply this equation down here to find out what the second virial coefficient of the mixture is. In general, if instead of having a binary mixture, you have more components, the equation to use is the one down here. It's just an extension of it. But see the beauty of it. Simply by knowing how two molecules interact with each other, you can extract the second virial coefficient for very complex mixtures. But you need to know those potentials. You can do the analysis, and you can get information also for the third virial coefficients. It's the same derivation, the same sort of approximation we made earlier, that the interaction between triplets is the sum of the pair interactions. But the beauty, again, is that statistical mechanics tells you how you can extract those virial coefficients by knowing how the molecules interact with each other. So I cannot stop repeating that. It is an extremely important point, and in many equations that are available in the literature, we may have many parameters, but we do not know in general how those parameters depend on the interactions between the molecules. In this case, we do. So let's go back to our virial equation truncated to the third coefficient. So this is the expression of the equation that we have, and earlier, at the beginning of this recap, what we saw was this equation that comes from classic thermodynamics, in which we can extract the fugacity of the component in our mixture if we know the equation of state of that mixture all the way from ideal gas behavior to the conditions that we are interested in. Okay? So now what we can do is to say, well, why don't we take our virial equation of state, we calculate the derivative of the pressure with respect to the number of moles of component I, keeping everything else constant. Then we do the integral, and we calculate what will be the fugacity coefficient for my component in the mixture. Right? There is a lot of algebra, a lot of maths in here that, of course, I don't like to do, but somebody else has done it for us, and the solution is the following. that we have a very nice, simple expression for the fugacity coefficient of the component I in the mixture as a function of the molar volume of the mixture, which you can obtain from the virial equation, the Bij's between all the molecules in the system. So this is the sum of all components from 1 to m. So it includes also two components that are the same. So II is included. The y's are the mole fractions of each of the components in the system. So once you know what the composition is, you know already the Bij's because you know how the molecules interact with each other. So you're taking care of this part. Here you also have the molar volume of the mixture, the square power. Here again you got your compositions of the system, and the Cijk is the third virial coefficient between the three molecules that you are considering in these two nested sums. And this is the compressibility factor of the mixture at the conditions of interest. So again, if you have your virial equation of state, it tells you what that compressibility factor is. So simply by knowing what are the second and third virial coefficients between the various molecules that you have in your system, you are able to calculate the fugacity coefficient for those molecules in the system. Right? So this is a little bit of a quiz for you to try to solidify the concept, but the point is again that you are able to obtain these values, but you just need to be careful to take into consideration all the molecules that you have in your system and to extract the virial coefficient that describe each of the various interactions. Okay? Now, we've done it for a general mixture that contains many components. If you want, you can rewrite it for a binary mixture, and this is what the coefficient looks like. Symmetrically, this is written for the component 1 in the mixture. Symmetrically, you can write it for the second component. And what you can notice is that B12 is equal to B21, because if this molecule I and this molecule J, and they are interacting with each other, you can replace their names, and J and I interact with each other, and the way you calculate the virial coefficient by the integral of the potential is not going to change. The two are symmetric. And for the same reason, if you now consider triplets, the C122 is equal to the C212 is equal to C221, simply because you can exchange the position of the particles in that triplet. Right? So now you know how to calculate the fugacity coefficient for component 1 in a binary mixture. So a couple of comments. This is a very important equation because you are now able to calculate this fugacity coefficient in a mixture. It is theoretically derived. We did not make any hypothesis. The only assumption here, the only little thing that we made was that the interactions between three molecules is the sum of pairwise interaction. And it is just an assumption to make our life easy. Statistical mechanics will not need that assumption. Okay? Other than that, there is no limit. You can use multi-component systems. This equation is always going to be valid. The only problem is that it's only good as long as the virial equation is good. And the virial equation of state is good up to moderate densities. At larger densities than that, you cannot apply it, because if you go back here, where is it? This integral has to be conducted all the way from zero pressures to the pressures of interest. So the moment you are deviating in between your equation of state and the reality, you are beginning to introduce errors. Okay? Now, next is to use these to try to see if we can validate the models that we have derived in the prior discussions during this model. Right? So how do we do this? Before we talk about the models, let me talk just a little bit about experiments. We have seen the virial equation of state applied to a binary mixture and how you can extract the fugacity coefficient of the first component. Now let's assume we are still looking at the binary mixture, but we go to the limit at very low pressures, in which we actually don't need to use the third virial coefficient. So we can stop the equation and we don't need this part over here. Right? That is what I'm writing over here. I am looking at the equation, a virial equation that is written for a system. It can have actually multiple compositions in there, but I look at the limit at very, very low densities where the second virial coefficient is enough. Then I can do the same approach. I can put it into the equation. I can find out what is the Fugasti coefficient of my components in the system, and I find this equation over here. Now, if I look at the binary system, so there are only two components, and I'm already at very low pressures, but now I also go to a different case in which one component, that component I, is at infinite dilution, so it's maybe 1%, maybe less than 1%, into the component J. So now I can take this expression and I can simplify it for a system that is, for the most part, J. Then if you do the analysis, what you find is that instead of having the molar volume of the mixture, you can have the molar volume of component J, because it's mostly J, 99+% is J. Instead of having the compressibility factor of the mixture, you can have the compressibility factor of the pure J at the same temperature that you're looking at very low pressures. And now here, when you have I, the mole fraction of component I becomes very, very small. So that part is not really doing much, so you can bring it down to 0. On the other hand, when you're looking at the y of j, the mole fraction of j goes almost to 1. So you substitute 1 for it. And if you do that, then all you have is that the natural log of the activity of the Fugasti coefficient of component I at infinite dilution in j is equal to this expression over here, where this term and this term here are properties of the pure j. So you know them. You can do experiments if you like, but they're easily found. And what you're left with is the virial coefficient between I and j, the second virial coefficient between I and j, that tells you how the molecule I is interacting with the molecule j. So this is a very important experiment. It's done usually by chromatography that allows you to figure out how one molecule type I is interacting with one molecule type j. Okay? It tells you, however, not how the potential looks like as a function of distance. It tells you how the integral of the potential as a function of the distance looks like. Okay? So that experiment tells us what Bij looks like. What our theories that we discussed earlier tell us how the potential between two molecules change as a function of the distance. Now we have done an experiment that we can extract this Bij. What we can do is to compare, we can put inside of here a number of equations that tells us how that potential change as a function of the distance. We can do the integral, we can put 2 pi Avogadro number in front of it, and then we can compare the outcome of our integration, which is our, if you want, our hypothesis of how two molecules interact with each other. We can compare that with our experimental evidence that tells us how big or small that Bij is. Okay? Will we be able, using the simple expression like Lennard-Jones, that describe interaction between pair of molecules, will we be able to extract all the experimental observables in terms of that second virial coefficient? All right, that's what we're trying to do in this moment. If you want, I can give you a quiz. So figure out what this Bij is when the interaction potential is described by this equation over here. So think about this and we'll go through it in our tutorial if we need. Now, these are a number of pair potentials that you can find in the literature. This one is the Lennard-Jones potential that we discussed earlier. So the 12,6 form of the Lennard-Jones potential look like that. If you remember, the Mies potential has different ways to change the curve, but more or less it looks very similar. This one is the potential that identifies an ideal gas, so the two molecules are actually not interacting with each other. This potential here is describing an hard sphere, so two hard spheres don't interact when the distance is large, but when they touch, the potential goes to infinity immediately, they bounce back. It's basically when a billiard ball is considered and it is bouncing around other billiard balls, that's what happens. And these are other type of potentials. This is the square weld, which was very useful at the beginning of the simulations because it doesn't take much computing power to use this in simulations. And it's very similar to the hard sphere. Interaction is 0 when the two molecules are very far apart, infinity when they are touching each other, but when they are at intermediate separations, there is an attractive potential that is described by this epsilon, and this attraction is valid all the way of r that multiplies sigma, usually that r is 1.5, 1.2, 1.3, which determines the width of that weld. All right, so these are all forms of potential that you can come up with. Is any of this real? That's the key. We discussed earlier the Mies potential, which is where the 12.6 Lennard-Jones potential come from. We discussed how you can change that the value of that parameter 6. We like it because it represents dispersive interactions at large distances. Dipole-dipole interactions, they scale with the 6th power, so that's where it is. The n, however, as we discussed, we don't know that as much, so we typically put it anywhere between 9 and 18. You can usually put whatever you like. Lennard-Jones like to put 12 in there. And these will be different ways in which we can change these interaction potentials. Before we go any further, I want to bring to your attention a paper that comes from the Imperial College group, George Jackson, Claire, Amparo, Harich, and their group. Carlos is now at Manchester, and Tom is here in London working for a company. I actually don't know where Anastasia ended up, but who knows. And I like this paper. It's now a few years old. And the reason I like it is that it discusses the Mies potential, so you have a little bit of a practical insight of why this potential is important. But I also like it because it gives you an historical overview of where these various potentials come from. And in particular, they talk about the 12.6 form of the potential. And what you can see over here is that this is a sentence that was taken from a person that wrote this in 1954, so more than 50 years ago. The only conclusion that can be drawn from the body of existing work is that a potential function more realistic than the Lennard-Jones 12.6 potential must be chosen if consistent information about the intermolecular forces is to be derived from the various physical properties. All right. So in other words, already 60 years ago, we knew that the 12.6 Lennard-Jones potential was not really good, but we still use it today, a little bit because we are familiar with it, a little bit because it's easy to put in the various software, and a little bit because we are a little bit too lazy to change it. And what George Jackson and his colleagues did was to show us that if we allow for those parameters to change and not to be just fixed to the 12 and the 6 values, we will be able to get better reproductions of experimental properties. Right, I'll let you read the paper. Let's go to the ideal gas. So the potential is equal to 0 as a function of the distance. So now if you write 0 here, what you have is that the exponent of 0 is 1. So 1 minus 1 is 0. And the integral is 0 over a very large distance is going to give you 0. So in the ideal gas, the second virial coefficient is equal to 0. And if you think about it, if you take the virial equation of state, and if you plot that the coefficient B is equal to 0, this goes away, and you recover your ideal gas law. Right? Of course, it's only valid for very low densities, so it's at the limit, and we know that it is the limit behavior, and the reason is that when we have real gases interact with each other. Okay? For an hard sphere, the potential looks like infinity when the distance is less than the diameter of the particle, or 0 when the distance is large. So now we have our integral to solve, which is down here, and we notice that the exponential can be 0 when the potential is infinity, right? The exponent of minus infinity is 0, or it can be 1 when the distance is larger than sigma. The exponent of 0 is 1. So what we have this integral that from 0 to infinity. What we do, we split the integral from 0 to sigma and from sigma to infinity. From sigma to infinity, that integral is going to be equal to 0, so it doesn't do much. But from 0 to sigma, we are going to have 1 over here. So it becomes the integral of r squared in dr from 0 to sigma. And in front of it, we got 2 pi and the Avogadro number. All right? And if we solve that integral, what we find is that the second Virial coefficient for the hard sphere gas is given by this value over here, which is equal to 4 times the particle volume. Notice it's very simple, so it's useful. It tells us something about the size of the particles. If we compare this value to experiments, we see that it doesn't change with temperature. It's always the constant. But in reality, experimental data tells us that the B changes with temperature. So it's not really a very good representation of the reality. But the advantage is that it only has one parameter, that's sigma. So, it can be useful in some circumstances. And if you're interested in systems at very, very large temperatures, well, maybe it is a good representation. Okay? If we take this is the same analysis, but now instead of looking at the two molecules that are the same, there are two different molecules. So the Virial coefficient between I and J is going to be equal to this value over here, where instead of having the diameter of one molecule, we have the average of the diameter of the two molecules. If we take something that a little bit more realistic, is the Sutherland gas. The potential is infinity at distances less than the diameter of the particle, and it scales with one over the distance to the 6th power, and there is a proportionality constant in front for larger distances. So this part takes into consideration of dispersive interactions, and this part takes into consideration of hard spheres, of the hard volume of a particle. To solve the integral, we split it again between 0 and sigma, and from sigma to infinity, and now we can solve it. And what you see is that you have now two fitting parameters. One is the sigma, and one is the k. So by fitting those two parameters, you are able to reproduce better experimental data. So you have more flexibility. So that's very good. So it is a better representation of reality. However, if you use this potential to look at how the B changes as a function of temperature, what you would find is that it reaches a constant value, but experiment shows some sort of a maximum at large temperature. So it's not reproducing entirely the physical reality, but it is a good way to start predicting behavior of fluids. Okay, so in most cases, it's fine. The Lennard-Jones, it's now more complicated. You still have two parameters, though. You have the sigma and the epsilon. But now you need to do numerical approaches if you want to integrate this. And it is a little better representation of the reality. It does show a little bit of a maximum in the B that you predict as a function of temperature. So it is a better representation of reality. Okay, but you do need numerical ways to integrate this. So if you plot this B as a function of temperature, the curve looks like this, and it's okay. Okay. In fact, many people in the literature have tried to reproduce experimental data using the Lennard-Jones expression, doing exactly this. They took the second Virial coefficient from experiments, and they changed the parameters sigma and epsilon until they're able to find a good representation of reality. So in this table here that I took from the Prausnitz book, you get the value for the sigma and the epsilon that are able to reproduce argon, carbon dioxide, and other molecules. So using these values, you are able to find values for the densities of this system that are able to reproduce the experiments. Okay. However, the question now is, are these parameters good? Well, here, what you see is that there are two parameters, and you can do one experiment at a given temperature. So you can, if you have many, what you can do is that you can select one parameter, say the sigma. You take an experimental data at 300 Kelvin. You fit sigma and epsilon, and then you say, okay, now I keep this sigma constant, and I take another experiment at 350, and I change the epsilon so that I'm able to reproduce that experimental data set. And you keep on going, keeping that sigma constant and reproducing experimental data as a function of temperature. And then you do another procedure where you take the data at 400 Kelvin, you get the sigma there, and then you change the epsilon accordingly to fit a number of experimental data at different temperatures. And you keep on doing. And you can do it for several cases. And what you saw basically as a function of the epsilon, you find the different values for the sigmas. And, you know, what you will, if there was a combination of sigma epsilon that was able to describe every single conditions, all of these ways to extract the parameter will eventually converge into the same condition of sigma epsilon. But instead, what you see is that there is a region over here where all of these lines converge. They overlap to some extent, but there is not a single point. So what that tells us is that sigma epsilon parameters that are confined in that region, they should do a decent job in reproducing the properties of the system, but they're not unique. That lack of uniqueness tells us that we don't have a very clear understanding of the interactions between the molecules. So this Lennard-Jones potential is not the real way in which those two molecules interact with each other. That's the meaning of this graph. We can keep on going. There are other potentials, for example, the square well, where you have now three parameters. You have the sigma, you got the r, and you got the epsilon. And of course, that allows you to reproduce even more experiments, although this approach does not give you the maximum at high temperatures, but still it's good. The exponential 6 gas, it has now the exponential form here is a significant advantage in the sense that it can better, it has some physical meaning in describing the repulsions between two molecules when they're very close to each other. So it is an attractive potential. There are three parameters. You can still put it into your equation for the virial coefficient and extract what the virial coefficient will look like. The Kihara gas complex equation, still very useful. The three parameters as well. So it has the ability to reproduce many more experiments. These are the potential look like. And, you know, it kind of matches the expected electron density for various systems. So it's attractive. The people have used the Kihara potential to reproduce experimental data. These are the parameters that they found. And again, they're able to reproduce the properties of argon, the properties of carbon dioxide, and other systems. So it's all good. However, the question is always back to the same. Do we have a single potential that is able to reproduce the experiments? And, you know, in this figure over here, what I plot, I took it from Prausnick's book. All of this potential, the square well, the Lennard-Jones, the Kihara, the exponential 6, all of these potentials have been fit to reproduce the second virial coefficient of argon. So they do an excellent job at reproducing the second virial coefficient of argon at a given temperature. So from that point of view, they're all equivalent. The problem is that they're all different. So which one of these four potentials is the one that is truly describing the reality? And the same story can go here for neopentane. And the same story can be repeated for many other molecules. So the point to remember is that yes, we are able to reproduce some experimental data, but we don't have a unique function that reproduces those experimental data. And if we were to look at other type of experiments, diffusion coefficients, for example, or other things, we will still be able to reproduce them, but the parameters that we extract to reproduce those properties, in general, are different than the parameters that we need to reproduce second Wheeler coefficients. So, yes, we are understanding how the systems behave, how the molecules interact with each other. We have the statistical mechanics approach that tells us how to go from the interaction potentials to the second Wheeler coefficients, but we lack a little bit of understanding of those interactions. All right? So I leave that with you, and to conclude, I want to show you an experimental piece of work. This comes from UCL, just actually 10 years ago already. And basically, this is an experimental work that was done to try to better understand how benzene molecules interact with each other. And what they did was they took liquid benzene, they did experiments, they extracted the way benzene molecules accumulate next to each other. Then they conducted simulations for model potentials, and they kept adjusting the interaction potential until they were able to reproduce the structure of the liquid. So I just wanted to leave it with you to give you a feeling that we are making a lot of progress in understanding how molecules interact with each other, and we are trying to understand how those interactions will reflect into macroscopic quantities. We are working on the statistical mechanics approaches to make those connections consistent, but we are still trying to better understand how these molecules interact with each other. And these days, people are doing a lot of advancements, also in artificial intelligence applied to force field derivations to try to help us get better potentials for these systems. All right, with this, I stop, and I hope you found it interesting. Thank you very much for your attention. Let's see if I manage to press that. And stop recording. Bye-bye.